Thanks, Vlad, for the introduction, and thanks to everybody for coming out in this cold and rainy night there in England, which of course you're not really going out. You're all sitting in your warmth of your home and hopefully having a nice drink and something to eat during the talk. So as Vlad mentioned, I'm going to talk about work I've been doing, historical work relating to the intersection between photography and atmospheric science. And in fact, this work is the basis for a book that I'm writing for the American Meteorological Society, which hopefully will be completed at the end of next year. And this is the title of the book. And there are two things that really thread throughout all the chapters, two questions basically that tie them together. One is, how has photography advanced understanding of atmospheric science? And how has atmospheric science propelled new photographic technologies or found new applications for existing technologies? So this is the cover of the book. Just have to finish some of the interior stuff. And here on the right is a listing of the chapters. The things I've highlighted in blue are some of the topics I'll just touch on this evening for you. So I'll talk about the birth of photography and its relationship to science. I'll talk about how photography was essential in the discovery of atmospheric ozone. I'll talk briefly about clouds and galloping horses, and you're wondering, how do those two things connect? I will show those things to you later. And I'll finish up with some work done by Wilson Bentley about a century ago, dealing with the photography of snowflakes, raindrops, and aerosols. And of course, the book has many other topics in there. And when it comes to weather, climate, and photography, there are hundreds, if not thousands, of books that you can find on Amazon. The vast majority deal with what I would call pretty picture books, the coffee table books of extraordinary weather phenomena. Now, of course, I'm very much interested in that, and there are some striking images that are in the book, but I'm also very much interested in that real deep intersection between photography and the science of the atmosphere. How these two things formed a symbiotic relationship and how they really have led to developments in both fields. So that's the basic idea behind the book. So to try and anchor where we are in terms of various discoveries relating to photography and atmospheric science, I've just given you a very brief chronology here. So if you're ever on a game show, I'm sure you have those over in England and elsewhere around the world, and you're asked, when was the birth of photography? Well, you'd press your buzzer and you would say 1839. So 1839 is recognized as the year for the birth of photography when it was announced to the world. The first aerial photograph was made in 1858, and it'd be hard to imagine not having aerial photography today, especially if you're a meteorologist, where we rely on satellite imagery to give us information over much of the globe where we don't have direct instruments to measure what's going on in the atmosphere. The United States Weather Bureau founded in 1890, discovery of the stratosphere in 1902, stratospheric ozone layer in 1913. In fact, the discovery of the stratosphere and the ozone layer, photography played a major and essential role in those discoveries. First photograph of the stratosphere-troposphere boundary was made by a balloon in 1935. The theory of Rossby waves, these are large-scale circulations in the atmosphere, which really is the foundation of what we consider modern dynamic meteorology. And the first photograph from a satellite, 1959. So photography, meteorology, that relationship in terms of the major advances is relatively new compared to many other branches of science. And so I'm going to touch on a couple of things that hopefully will amaze and surprise you about that relationship. So let's go to 1839, Paris. Rumors had been circulating already about what one paper referred to as the secret of the perfect invention. And so when the meeting at the Academy of Sciences in France was set up, these rumors were swirling. What is this secret invention? Well, the secret invention was this process for making images solely through the action of light. And one of the people who participated or was there at this announcement wrote, "Truly a victory, a greater than any bloody one, had been won, a victory for science." So right from the outset, it was recognized that photography would play an important and major role in science. Now, of course, when it first was introduced or announced here in 1839, there was still a lot of technical glitches and things going on. So photography wouldn't really supplant drawing in science until another 50, 60 years, but it was evolving throughout that period. This is a sketch here of that meeting in France when photography was announced to the world. And this is one of the photographs purported to be present there that Louis Daguerre had and made with his new process. So you can see it's really quite good. This Daguerreotype, as it was called. So a picture of his atelier, and again, pretty good detail. So it really astonished the world when this was announced and people saw what it could actually do. So 1839, but in 1824, here you have Daguerre saying, I seized the fleeting light and enchanted it. I have forced the sun to paint pictures for me. Very eloquent, very poetic. But that exuberance was premature. He was producing pictures, but they weren't permanent. They faded very quickly. So he wasn't able to what we call fix the images, but he was on the right track. So 1839, his process, what was called the Daguerreotype, was announced, and months later, William Fox Talbot was stunned because he was working on his own independent process, and basically Daguerre scooped him by several months. But Fox's or Talbot's process is really the ancestor of modern photography. Daguerre's process was on a silver-coated copper plate, very difficult to make copies of those kinds of images. Talbot's process was basically on paper, had a negative positive process, so very much really the ancestor of today's photography. And he wrote, I do not profess to have perfected an art, but to have commenced one, the limits of which it is not impossible at present to ascertain. Boy, wouldn't he be surprised today for us to have a phone, make an image and send it around the world. So very prophetic, very poetic types of statements about this new invention by two of the giants in the field. I'm going to give you a couple of quotes to provide some context of what the thoughts were during the 19th century. This is a quote from 1872 by Henry Pritchard, who said, the accuracy and fidelity with which the pencil of light performs its function, combined with the facility with which such reliable records are obtained, make photography indeed one of the greatest boons at the disposal of scientific men. And another person who emerges in the history of photography who's quite a character. I recommend reading up on him. He's really quite flamboyant and quite interesting. His statement was, which he made in 1857, a year before he made the first aerial photograph from a tethered balloon. He wrote, photography is a marvelous discovery, a science that occupies the highest intelligences, an art that sharpens the most sagacious minds, and the application of which is within reach of any imbecile. Okay, so basically what he's saying, and this is probably even true today, that it's very easy to make a photograph. You pick up a camera, you point it at something, press the shutter, you get something back. But the question is, are those photographs meaningful? And John Sarkowski, who was the curator of photography at New York Museum of Modern Art for many years, said it's very easy to produce a photograph, really that's not meaningful, kind of boring, but produce a photograph that is meaningful and stands the test of time is almost impossible. So that's the dilemma of photography. Irving Penn, in modern days here, modern photographer known for his great work, wrote, and I think this is quite apt, the camera is part Stradivarius, part scalpel. So of course it takes a skilled person to play the Stradivarius or to work with the scalpel, and the same is true of photography. So I'm showing you here two cameras. They basically have the same way of operating, just different in size. The one on the left is the Daguerreotype camera around 1839. It simply had a light-sensitive material within that box, the Daguerreotype. It was a light-tight box, and it had a lens for focusing the light and a little lever in the front that controlled the length of the exposure. Now, the camera on the right, that's a little bigger than our phones in terms of carrying it around. It was called the Mammoth camera. It weighed 1,600 pounds, and it was designed to make photographs of railroad cars for the tourist industry in the American West, to get people on trains moving out west. So they produce these very large photographs they put up in the train depots. But its basic design is the same as the one on the left, and it's the same as what we use today. Again, some light sensitive material in your camera. It could be a digital sensor, it might be chemically based material. You need some lens to focus it and something to control the exposure. So irrespective of the size of the camera or what we're using today or in the past, they really have the same basic ingredients. Basic recipe is the same. So in dealing with photography, of course, we're dealing with light. In fact, the photography derives from the words photo and graphos, meaning writing with light. So light is the photographer as clay is to the sculptor. It's what the photographer uses to mold and make images. And so for us, it's the sun that produces the natural light, this ball of energy. And that energy comes in the form of what we call electromagnetic radiation, which has a very large span of wavelengths. Over that whole EM spectrum, there is only a very small portion that we're able to detect with the unaided eye, and that is called the visible spectrum. That's where we see colors. And the spectrum, the radiation itself doesn't have color. It's what our optic nerve, our brain, and our eyes do to convert wavelengths, these specific wavelengths, to sensations that we associate with color. So one of the challenges early on in photography was to try and capture some of these electromagnetic waves that were outside the visible range, what they called at the time the invisible rays. But it's this light that really is what is worked with in photography. It drives the Earth system in terms of energy, and it's the quantity that we work with in photography. I'll show you this photograph before I get into a couple of details because it's one of the most famous photographs in history. It's called the Blue Marble. It was made by the crew of Apollo 17 as they were hurtling towards the moon in 1972. Why is this so famous? It's the first time that fully illuminated Earth was photographed by a human holding a camera. People hadn't seen this before. They'd seen part images of the Earth, different phases. But for a few moments, as they were traveling at 17,000 miles per hour towards the moon, they could see the fully illuminated Earth. They picked up a Hasselblad camera and made 3 images, and this is one of them. So why is this so famous? Well, like I said, it's the first one made of a fully illuminated Earth by a human, but also it really helped spur the nascent environmental movement. It showed the Earth in its beauty, sitting and floating in the black abyss of space. And for the scientists, we got a really great view of the Earth. To the upper left, you see the Sahara Desert. To the far right, you see a little swirl. That's a tropical cyclone off of India. Towards Central Africa and down a little bit, you see these puppy-type clouds, indicative of the convective processes operating over the tropics. And if you move further south during Southern Hemisphere summer, since it's December, you see these big, what we call comma clouds. These are associated with what we call mid-latitude storm systems. This is probably what you're getting in England tonight is a mid-latitude storm system. So from the art perspective, it was a striking image. From the importance to the environment, again, helped spur the nascent environmental movement. And for scientists, it really encapsulated the complexity of the Earth system, a complexity that still challenges scientists today in terms of weather and climate forecasting. So the first thing I'm going to touch on, I can't get into the details, that's all in the book, but it's a fascinating subject, and that is the role of photography in the discovery of atmospheric ozone. And this discovery is related to what we call the absorption properties of Earth's atmosphere. So this is about as technical as I get is in this picture here, which we often show in some of our introductory classes in atmospheric science. The yellow indicates the absorption as a function of wavelength of the sunlight without an atmospheric absorption. That is, if you put a measuring device at the top of the atmosphere, this is what the spectrum of absorption would look like. But of course, the light energy coming from the sun has to pass through the atmosphere, and some of that light energy is absorbed depending upon its wavelength. And of course, it depends upon the makeup of the atmosphere itself. So one thing I want to point out on the left here where it says UV, that column, you'll notice that at the top of the atmosphere, there is radiation coming in the UV part of the wavelength spectrum, but the red with absorption, you'll notice that all that radiation is absorbed at the surface of the Earth. So what is absorbing that radiation? Well, photography really answered that question. So let's see what they did and how they did it. So there are 3 gentlemen, 3 scientists who made 3 discoveries and resulted in the truth. And one was Christian Schoenbein, Alfred Cornu, and Sir Walter Hartley. Their 3 discoveries set the foundation for explaining the absorption of UV radiation in the atmosphere being due to ozone. And that was the basis for the eventual discovery of the stratospheric ozone layer. So let's begin with Schoenbein. I would love to write a paper. In fact, most of us would probably like to write scientific papers today that have this quote. This is what he stated in his paper. After doing a lot of useless experiments, of course, we don't say that today, but many times we would like to say that. And what his experiments eventually showed, that when he passed an electric current through acidified water, a pungent odor was produced, an odor that he called ozone, which derives from the Greek word ozone, meaning to smell. Now, of course, smelling that odor we associate with ozone was not new. That had been known for ages. We often smell that after a lightning storm. But what was new is that he associated with this, this process of forming this gas, if you will, through the electricity, which produced this chemical reaction. And he went on to write in his paper, I was convinced that this body, ozone, emerges in the air and in quite a significant amount when the weather is stormy. So that sparked a number of other studies. In fact, he spent much of his life making great advances in the study of atmospheric ozone. So this is kind of like the first step, if you will, the first building block. Then Cornu enters the scene. He carried out spectroscopic studies of light, and spectroscopy involves the interaction of electromagnetic radiation with matter. So what does that mean? Well, it involves the interaction of that radiant energy, which is a function of wavelength, with matter, which includes, for example, the atmosphere. It might include raindrops, snowflakes, anything that the light may interact with. One can do spectroscopic studies. And those studies allow us to understand quite a bit about the matter that is absorbing, refracting, reflecting that radiation. So the light, in terms of these spectroscopic studies, is broken up into its wavelengths through a couple of devices. One is a diffraction grating in the top, and the other is a prism. And most of us are familiar with the prism. We've done this in elementary school. You shine white light through it and breaks it up into the rainbow. And in fact, it's that same process that gives rise to the rainbows. As the light passes through one medium, air, into another medium, the water drop, the light is dispersed into its spectral colors that we see, forming the rainbow. So Cornu had this experimental setup, which consisted of his spectroscope, which consisted of a tube containing a collimating lens. This is a lens that when the light passed through the system initially, it resulted in the light beams being parallel. Before it passed through a prism, which dispersed the light into a spectrum of wavelengths that were recorded on a photographic plate, which was sensitized with what is called wet collodion. So today, of course, many of us were doing photography early, working with film. Of course, now it's digital. But back at this time, one of the techniques that was used, what was called the wet plate process. And you can see a picture on the bottom where you had a glass plate. You poured this collodion, which contained light-sensitive material in it. You coated the plate, inserted it into the camera, made the exposure, and when that dried, you can then make negatives from that. So through these experiments and through the absorption of light as it passed through this system, he discovered that the terrestrial atmosphere exerts on the short wavelength radiations an absorption so energetic that the greater part of the solar ultraviolet spectrum is intercepted in a complete way. So something was absorbing this wavelength of radiation. He didn't know what it was. He was unable to ascribe his finding to a particular absorber in Earth's atmosphere, but something was going on. There was a mystery here. What is it in the atmosphere that absorbs this part of the electromagnetic spectrum? That is what is absorbing the UV radiation. So that was the key question. So not too long after Cornu's study, Sir Walter Hartley enters the scene, and he did lots of innovative scientific research. And this quote, I think, is very apt, where he says, "My work led me to the conclusion that the spectroscope would never be made available for many of the purposes to which it might be applied until it had been combined with a photographic camera." Kind of makes sense, but how do you do it? So here are the challenges that Hartley and others faced. What camera systems do you use? Cameras weren't easily purchased off the shelf in the mid to late 19th century, especially if you're doing detailed kinds of experiments where you needed specialty cameras. What material should the lenses be made of? Seems like kind of an obvious, answer. Let's use glass. Well, the problem is glass absorbs the UV radiation, and you don't want to study the glass material, you want to study the gas. So one had to choose a certain material for that. Fortunately, a few decades before, George Stokes, who in a very incredible paper, 100-page treatise examining refraction properties of materials, found that quartz was basically transparent to UV radiation. And so at the time, quartz became the lens of choice for people, especially doing experiments like that of Hartley. How do you produce in a laboratory setting a light spectrum that contains UV radiation? Again, today, even our smartphones have a flash on them. We have artificial light, but take yourself back to the late 19th century. How do you set up a light system that produces a broad EM spectrum, so broad that it contains UV radiation? How do you produce the ozone in the laboratory that can be measured carefully? And how do you focus the UV rays onto the photographic plate? Remember, UV is outside the visible part of the spectrum, so we can't see it. So how do you focus rays that you can't even see? So there are a lot of challenges that had to be overcome to carry out these experiments and ultimately determine that ozone was responsible for absorbing UV radiation. So let's take a look at his camera system here. It was big, okay? So scientists at that time, like Hartley, had to be basically these master of all trades. And they had to make the camera, they had to know the chemistry, they had to know the physics of light. Now this camera he helped design, and of course it was made by people who had the skills to put the things together. So this particular camera was such that the camera body plus the lens was 5 feet in length. Okay, so it was a big setup and had to be placed on a very sturdy table to support this and avoid vibrations that might affect the sharpness of the image. Now, for those of you who are into photography, we know that one of the currency of how we talk about exposures and making photographs is the f-stop. The f-stop of his system was about f21, which means a very small aperture, okay, compared to what we have in our cameras today, which gives you what is called a large depth of field, that distance over which things appear sharp in your photographic image. So this camera system had the lens tube, had a certain diameter lens. And of course, given these dimensions, I could calculate and back out of that the f-stop and other information about the camera system. So you had a lens tube, you had the camera body within which was placed the photographic plate. And one of the innovations that Hartley came up with was a dry plate rather than the wet collodion used by Cornu, for example, which was really a cumbersome process. You had to make the image while the collodion was still wet. The dry plate process made it much more efficient and much easier to work with. So the plate was inserted into the camera. Between the camera and the lens, there was a bellows, which would be adjusted by a focusing knob to allow one to focus the image onto the plate. Now, in the upper right here, I sort of have this insert. So you had a light source, it passed through a collimator tube, again, to straighten the light rays, would pass through the prism, disperse the light into its spectrum, enter the camera, and of course, you could then measure what the spectrum was like, what wavelengths appeared or didn't appear, and therefore back out some information about the absorption properties of the gas between the light source and the camera itself. So what about a light source? Well, this basically was what the light source consisted of. It had Grove cell batteries, a bunch of them, which were connected to an induction coil, which converted that low DC voltage to high voltage through the AC. And the charge was stored in what was called a Leyden jar, so the ancestor of today's capacitor. And then that was passed to these electrodes, which produce a continuous spark. So Hartley's system was similar to that used by Miller, who carried out experiments with some photography and in general. And he stated a torrent of sparks could be maintained without any sensible variation of power for 10 minutes at a time or longer if necessary. So this was what generated the electricity, not only for the light that would enter the camera system for the exposure, but it's also necessary to produce electricity to produce the ozone. Okay, so this is basically what drove the light and the electricity for the system. And this is sort of a schematic. This actually picture is from Hartley's paper describing the process associated with making the ozone. And in the book, I can go into much more detail about all this chemical process. In fact, was beyond my chemical understanding. I went to a colleague who's a chemist and helped me walk through and try and get all the details about how the system worked. But basically, you had a reservoir of oxygen pass through this elaborate system. Electricity separated this oxygen to the oxygen into O, which recombined with O2, you form ozone. And again, there's a lot going on in this particular system, but eventually he can control how much ozone appeared in this collimator tube with these stopcocks. It would pass, and then the light, of course, would be absorbed by whatever gas was in there, in this particular case, ozone, into the camera system. So this is quite an elaborate, complicated system. And of course, reading these papers to me, going back to the 19th century and early, is just fascinating with the breadth of knowledge that these scientists had, their attention to detail, and how they were also engineers and tinkerers to set all these things up. So this system that Hartley set up, very complicated, from generating the light to the chemistry to produce ozone to the camera system itself. So what was he able to do? Well, he was able to explain what Cornu could not, that the absorption of UV radiation is due to ozone. The ozone absorbing UV radiation between 200 and 300 nanometers are known today as the Hartley bands. So very important to our study of climate change, where we have the concentrations of various gases changing. To be able to measure these things in spectroscopy is still a major tool of choice for many of these studies. So in one of his papers, he has this what I think is a great statement. I am also entirely of opinion that a spectroscope camera, such as I have been using, may become a valuable meteorological instrument because the UV rays are so exceedingly sensitive to the absorptive action of very minute traces of substances, not only ozone, but of course methane, carbon dioxide, and so on, and notably to certain traces of ozone. So this is 1881. So even then, recognize the importance of the camera with the spectroscope as a means for measuring the various properties of Earth's atmosphere. So let's take a little change of pace here. We'll move on to clouds a little bit. This is a great picture by Mitch de Browner. One of his images I'm using for the cover of my book, as I'd shown earlier. And he does spectacular black and white photography of storm systems over the Midwest of the United States. And of course, that's our tornado alley. So let's talk about clouds. So in 1905, Arthur Clayton, in fact, I think it was with the Royal Meteorological Society where he gave many of his talks, he had this statement: "We do not yet know enough about the methods of cloud formation, and especially upon the relationship between form and origin." A couple of my colleagues are cloud physicists, and they say, well, you know, this statement still holds in a lot of respects today, as people are still studying clouds and trying to understand their role in the climate system. So this is a very neat book on cloud studies by Clayton, which I have published in 1905. And he talks about his photographic processes. In fact, at some of the meetings of the Royal Society and photographic clubs in England at the time, being able to photograph clouds was kind of your challenge, because there was difficulty with the range of light with the clouds versus sky. So this was kind of your measure of expertise. How well could you photograph clouds? So before I jump further into clouds, you're wondering, why am I going to take a switch and talk about caves and pixels? So let's see why. So if you go back and look at some of these fantastic Paleolithic paintings and drawings in caves, you'll notice, for example, that one of the things that they depicted on these cave walls were horses, and spectacular images. This is a part of an image from the Chauvet Cave in southern France. Some great Paleolithic artist whose name we don't know painted these. And if you can, just go online and check out these images. They're spectacular. So from those early cave paintings of horses, it took nearly 30,000 years before we really understood how a horse gallops. In particular, the fact that during the gallop, there's a point where all four hooves are off the ground and underneath the horse. So it took a long time for that discovery to be made. It was made by Edward Muybridge, who carried out pioneering high-speed photography. It was said that once his pictures are produced showing how a horse really gallops, that artists, were upset, saying, all my life I've been painting horses the wrong way. That's not how they really should be depicted. But of course, people pointed out, that's the prerogative of an artist. You have the artistic license. You can interpret things as you like. So 30,000 years from the time these Paleolithic artists entered caves, to figuring out how horses gallop, to today, of course, with pixels and photographic imagery. So let's go to the mid 19. Well, this is the image, the sequence of images produced by Edward Muybridge. It was actually on what is now the Stanford campus, Stanford University. There was a racetrack, and the person who hired him to try and find this out was Leland Stanford, one of the railroad barons, famous here in the United States. And he had a debate with a friend, and his friend said, no, when a horse is running at full gallop, the hooves are spread out, front and back. And Stanford said, no, I think they're all under the horse at a particular instant in time. So they had this debate. Stanford, being as wealthy as he was, he hired Muybridge to try and come up with some kind of experiment to see how a horse galloped. And what Muybridge did was, around a racetrack in Palo Alto near Stanford, he set up a number of cameras with a tripwire with electromechanical shutters, and that as the horse went by, it triggered each shutter and produced a sequence of images, which now, which formed the basis of what we have now, and that's the motion picture industry. And so in this sequence of pictures, he showed what Stanford had suggested to his friend, that at some point during full gallop, all four hooves are indeed off the ground and under the horse. So what does this have to do with clouds? Well, here's a study from 1952 by Malkus, and it's a sequence of clouds, photographic sequence of clouds. And you could replace this with horses if you like, but it's the same kind of idea. You're looking at this cloud at different points in time. And what you see is, in the upper left, kind of a puny little cloud. And then if you go down to the lower right or off to the right, the cloud has grown and tilted to the right. Interesting, but what can it tell us about the atmosphere? So what these photographic sequences have shown and were able to describe was some of the forces operating within the cloud itself. So the tilting of the cloud and its vertical extent could tell you how strong the vertical motion was in the cloud. It could tell you how strong the vertical shear was, which tilted the cloud. And with that information and some of the fluid mechanical equations, they could back out information on what was called the form drag, or the drag of those clouds with the surrounding atmosphere. So that was information needed to properly model clouds, but these photographic sequences were essential to that. So again, these sequences, time lapse, if you will, of these cloud formations with photography provided some really insightful and really important information about the fluid mechanical behavior and development of clouds themselves. If you jump ahead to the around 2006, there are many other studies going on even today with photography and the depiction of clouds. This is a study of examination of clouds over the Catalina Mountains in Arizona, and several cameras were set up to try and get and understand the morphology of the clouds over the mountains during their development, to get some of the cloud structure. And of course, cloud development is very important. Not only produces precipitation, the cloud can affect the thermal structure of the atmosphere, radiation balance, all kinds of things. And it's one of the toughest challenges we have today in climate modeling, to properly depict on a global scale the various clouds and how they evolved with the atmospheric circulations. So what they were able to do with these stereoscopic images with multiple cameras is to give the shape of the camera of the cumulus cloud, use that information, put it into computer models, and try and compare how this cloud develops over certain meteorological conditions. Of course, they related to other information with wind flows, atmospheric humidity, temperature, all kinds of other variables. But the camera provided this morphology of the cloud, which can then be input into the model and then correlated with other types of meteorological information. So just another example of how photography is being used. So I'm going to wrap up here the last few slides dealing with what Wilson Bentley, known as the Snowflake Man, produced what he called these miracles of beauty, snowflakes. He wrote, "Snowflakes were miracles of beauty, and it seemed a shame that this beauty should not be seen and appreciated by others." So he was a farmer by trade and a scientist by passion. He didn't have any formal training, but very careful observationalist and detailed in measuring and photographing the variety of snowflakes. He sought to explain how crystal shape and raindrop size, he studied raindrops also, and the distribution are related to the types of clouds and their formation. So this was his system. Okay, there's Wilson Bentley standing next to his system, not too fancy. It had a very large camera with a bellows. There was a microscope at one end. He had a glass plate negative, dry plate. He had a tray containing snow crystals, which he's holding, and he had a focusing wheel for the microscope. So he jerry-rigged this whole thing up himself. This was not something he could, go to Amazon and order the system. This was something he worked on and developed himself. So the snow crystal transferred from the tray to the microscope slide with a broom splint. Nothing fancy there. He just had a broom, took the splint, and used that to very carefully carry that crystal to the microscope slide. A bird feather was used to ensure that the crystal was flat on the slide. It required a steady hand, and as he says here, I have never used liquor, tobacco, or any stimulants that affect the nerves. Okay, so he made a point of making sure everybody knew that. His exposures from 8 to 100 seconds, and they were controlled manually. His glass plate negative was then processed, and from that, a print was made. So this is a collection in one picture. You've seen these, you probably can even get these in some art museums, these pictures of all his crystalline structure snowflakes that he photographed. It's all put on to one picture here, just as a nice sort of art display. But his images were known not only for their aesthetics, but also for their scientific content. And so what that content is related to is, as you can see on the right here, we can now have a better understanding of the types of crystals and what they say about the relative humidity versus temperature and how they form. And of course, today people are using very advanced techniques and measurements and so on to get a better understanding of these snowflakes. So let's just jump real quick to, I think this is my next to last slide. So more recently, beyond Wilson Bentley, there are now systems that are being used to photograph these snowflakes and ice crystals. One is the multi-angle snowflake camera. The setup you see on the left here has a few cameras. There are lights, and when the snowflakes drop from the sky, they break the beams, which trigger the exposure for these three cameras, which again can give you the morphology or shape of these crystals. And here's an example of the types of hydrometeors that were photographed in free fall using these cameras, which had a 35 millimeter lens, 5 megapixel cameras. And again, this information is important because we want to get better information when, for example, we're using radars to detect the type of precipitation in clouds. And again, relating it more to temperature and other kinds of factors. So these kinds of shapes and crystalline structures really give different signatures in terms of radars, and we really want to know better how those kinds of things operate. So these are interesting experiments, but there is a method to the madness to try and understand better meteorological phenomena in terms of cloud formation, weather, precipitation, things of that sort. So I'm going to stop there since we're about 10 to 11. And if there are some questions, I'd be happy to try and answer them. If, for example, I don't get to your question, or if you think there are questions that you should have answered and forgot to answer, feel free to email me. Okay, so I'd be happy to answer them later if that works for you. So Vlad, you want me to stop sharing now, or?
That's fine. You can stop sharing. You can leave it if you wish. That's fine. Thank you so much, Terry. This was just unbelievable and extremely interesting, really. I love the scope and the historical coverage here. That's really helping understand, especially the ozone story, which to me was kind of unknown to until today, especially the historical element to it. I have my own comments and questions, which I'll keep for later, and I'd like to invite everyone who's tonight with us to share their comments or ask questions, and just continue the conversation with Terry. I'm happy with people who would like to ask questions directly without outside of chat, or just use chat if you wish to go ahead and ask anything.
While people are thinking of some questions, I can make a comment. One of the fascinating things that I've come across, and it's been reinforced over and over again as I'm writing this book, is how interesting the original scientific papers are from these people who did these studies over a century ago. How thorough they were, how in-depth their studies were, and how they made these really well-reasoned extrapolations of what might be occurring. I mentioned that for example, George Stokes did a study showing that quartz is really an excellent material for a lens. In fact, he tested many materials. And that paper is an astonishing paper. It's 100 pages long, looks at all types of materials, refractive properties, and he even talks about a thunderstorm that occurred and the light from that in his studies. And in his appendix even discusses and lays out problems that would be problems that people are working on even today. So really fascinating insights and work that many of these individuals did.
I've got a question.
Sure.
Yes.
Okay, so that was a fantastic talk. Really, thank you very much. I enjoyed it immensely. But you didn't mention my hero, who is James Glaisher. And he's kind of a hero, but not. So he made one of the very early pictures from a balloon.
Yes, I have a whole.
But he used, photography.
Yep.
Yeah, but he used photography before that to take pictures of instruments. They weren't mainly meteorological; they were magnetic. And he became closely involved with the Royal Photographic Society and was their president for quite a number of years. But in the end, they really kind of got rid of him because they felt he was making the subject completely scientific, but it wasn't looking at the art of photography. And of course, the other thing he did, he was involved with Snowflakes, and his wife, I'm afraid he didn't treat very well.
Yeah, I'm glad you mentioned James Glaisher. He figures prominently in one of my chapters on aerial photography, measurements of the atmosphere from balloons and photography from balloons. So I have, he figures very prominently in that chapter, which I didn't have time to talk about.
For that photography in the Royal Photography Society, they call it the glacial period now.
Okay, cool.
Fantastic. Thank you for that. Other questions?
I think I have a question.
Irina, yes?
Yeah, thank you very much for such a nice talk. Although I have missed like 30 minutes because I have registered myself lately. So the question I have is concerned with feelings as atmospheres. Can you comment on this a bit? I mean, some pictures you have depicted, I mean, you have shown during your presentation, are they correlated to that theory concerned with like feelings and as atmospheres, or anthropological investigations of how people feel, and then they take pictures and then they investigate atmosphere as something geological, for example, and then it turns out to be something like the fear de sens or something like in another metaphorical thing. Yeah.
Yeah, if you go back to the 19th century, one of the motivations for a lot of these studies, I think, in science in general, has been the aesthetic qualities of the world around us. One thing I didn't mention is when Hartley produced his experimental evidence for ozone being the absorber of UV radiation, he then went on to address issues stating, or at least inferring that, well, perhaps the sky is blue because of ozone, because it's a pale blue gas. And he was wrong on that, but there were other studies dealing with why the sky is blue. So I'm not sure if I understand your question, but a lot of the motivations for these things were aesthetic motivations to try and understand these interesting things. You know, why is the sky blue? Why do clouds have these shapes? The nature of lightning, its awesome power. So it's those natural things really for scientists, especially then, and I think even now, motivate a lot of the work. In fact, my getting into meteorology and atmospheric science for a career was based and started when I was in junior high school, because I was fascinated by storms. To me, they were monsters. How did they form, their beauty and the clouds and all those kinds of things. So So I'm not sure.
Yeah, thank you very much. But I have just came up with some clarification of my question. When you try to approach atmospheres like in geological sense, which I mentioned, you come up with them from the third phase register, but when you feel them from the inside, and that was my question. That was what my question was about. Like, how can you approach such kind of atmospheres in geological sense without like switching these registers, like from your inner self to outer self, like the nature and something like this? Yeah, maybe you can just.
Yeah, I'm not sure if I fully understand the question. When you say geological, I'm not sure how you're relating that to the atmosphere. You mean meteorological or?
Yeah, I mean, in scientific way, when you just like it's some kind of qualitative research, not when you do it scientifically, not as a phenomenologist or in an aesthetic sense. So you have just numbers or I don't know, tables or measurements. When you perceive it, I mean, atmosphere, you come out of your house and see them, you feel them. And that's another approach. So you have a kind of a gap, I think, between these registers, like from the first phase and from the first place, which is yours only. So
okay.
that was
so if I understand, basically, like if you come out of the house and you see the spectacular cloud, where you get this kind of emotional response to the aesthetic beauty, how might that be related to when a scientist then turns that all into numbers and tables?
Yeah, specifically something like this.
Yeah. I don't think they're mutually exclusive, in a sense that for the scientist, by understanding that beauty, it oftentimes enhances our appreciation of that phenomenon. And again, I think many of the scientific studies are born out of those emotional responses to what we see around us. Then, of course, scientists tend to turn it into cold, hard numbers to try and understand it. But yeah, so I don't think they're mutually exclusive, but they kind of reinforce and work together sometimes.
Thank you.
Yes,
You're welcome.
Alan.
When you showed the difference between the theory and the experimental spectrum in the ozone end, and they started looking for the ozone problem, how did they measure that end of the spectrum in those days?
There's a technique that one can use to see. At that time, they could only do the absorption. They didn't know what the spectrum was at the top of the atmosphere.
Yeah.
They just knew when they looked at a spectrum, something was missing. Why did it abruptly change? There was a technique, in fact, I talk about it in the book, where one could infer based upon absorption at the surface what was happening above, but that wouldn't come until the early 20th century. But at the time when Hartley was doing his work, Cornu and so on, they didn't have the information at the top of the atmosphere. They just knew when they're looking at a spectrum, they'd expect it to be kind of continuous, and then it disappeared and they didn't know what was, absorbing that. But you're right, they didn't have what was going on at the top.
How did they measure the ultraviolet frequencies in those days? They didn't have photomultipliers and stuff.
No, just by wavelength. They just saw what wavelengths they were getting in the spectrum and what was missing.
Okay.
So that was the extent of that. In fact, one of the interesting things I mentioned, but I didn't follow up on, is one of the challenges. How do you focus the spectrum, especially the UV part of the spectrum, when you can't see it?
Yeah.
And what they did, this is a very ingenious thing that Hartley did, and it was based on work by George Stokes, was he took the photographic plate and covered it with a phosphorescence material. And phosphorescence is such that when light hits this material, this phosphorescent material, it re-emits light at a longer wavelength. So when the UV hits this phosphorescence, it radiates at a longer wavelength, which you could then see. So what Hartley did was he covered this plate in this phosphorescent material, put it in, and when the light coming through the camera system hit it, it re-radiated at a longer wavelength, which he could see, and then he focused it. Then he took the plate out, and then he put in the photographic plate. So that's how he was able to photograph a part of the spectrum that was not visible to the unaided eye.
Very clever, thank you.
Mhm.
Thank you.
Mhm.
Do we have further questions, comments, and ideas? I'd like to ask a couple of questions, some of which I've been thinking for a while myself, especially working on the clouds of the English painter John Constable,
Mhm.
which we all certainly know a lot. It is known that Constable in the 1820s has done a series of cloud studies up in his not far from his house in Hampstead Heath in London, where he would go out on a field, look in the sky and try to jot down and sketch the clouds as they were passing. And one of the things that historians of art have noted is he was effectively trying to capture the movement and the change of clouds and learn about what makes a cloud a visual entity, and then to try to translate that into his later large 6-footers, the big paintings. And there has been an argument for many years that whether his work on cloud studies and his attempt to perfect the kind of veracity of how clouds actually look has actually translated into his art and improved his ability to, quote unquote, represent the sky more realistically. The issue of realism versus non-realism in Constable is also kind of been a chronic issue. Now, I wonder if I'm going to ask you a question. Do you think that Constable, but also other artists, also probably not Turner, was not very much interested in showing these things in kind of any realistic sense, but do you think that Constable would have liked to have a photograph of these clouds and work, or do you think that what he was doing was not really photographic in nature, in the sense that he was trying to capture this particular moment? How would you describe the attempt of an artist to capture a particular moment in the sky versus the automatic kind of objective, almost aggressive way in which the chemical, the colloidal solution is helping us to capture what's out there without any selection process, just whatever light inscribes on that solution? Do you think that John Constable would have liked to have that photograph with him?
I'm not sure about that, but I think John Constable had an advantage, and I talk about him in my class in the photo art and science. I present his work. An advantage in the sense that when he's viewing these clouds, he has binocular vision. He can see kind of he can see better the morphology and shape of the evolving cloud. When you make a photograph, you're taking the scene and you're looking at the scene basically with one eye, looking through the camera, and that scene is then projected onto a flat surface. So you oftentimes lose that more three-dimensional structure in a photograph. And there are techniques in photography where we try to resurrect that feeling of three-dimensionality through wide-angle lenses, through various visual indicators of converging lines and vanishing points and things of that sort. So in some ways, I think Constable probably has an advantage if he, as a keen observer, in some ways over the photograph. And in fact, I think I just mentioned briefly at the beginning of my talk, at the outset of the invention of photography, people were recognizing its potential importance for science. But it took many decades before it became good enough to supplant the use of drawing, for example, in visual imagery in science. In fact, the first photograph of the solar spectrum made in the early 19th century, mid-19th century, is very rough. I didn't show it, but it's a very interesting photograph. When that photograph was eventually received by John Herschel, he published a paper on it, but what he did was he redrew that photograph so he could depict more accurately what the spectrum looked like. So there was a case where the photograph, okay, that was an interesting technical challenge, produced the first image of the photographic spectrum, but Herschel had to then go and draw the spectrum to really show all its nuance, which the camera could not capture. So I think Constable may have had an advantage in that sense, that as a keen observer, he could probably indicate things that you couldn't see with the camera. Now, another example is, I like occasionally going bird watching, and I have different bird books. Some use photographs, some use drawings. And I often find the drawings are better. With a little more detail, the photographic imagery might not have the right contrast, various things. So even there, even today, there are different ways of depicting a scene from the artistic drawing perspective versus the, like you say, the cold, hard capturing of light by the camera.
Thank you, Terry. Just to follow up on that, if there are no other questions, I would like, coming back to the clouds again, but not necessarily talk about clouds only. The cloud atlas and the photos of the cloud atlas. I was always intrigued by what is being photographed in the cloud atlas. Yes, these are individual clouds that existed at the time when they were photographed. But what a photograph was taking, like scores or atlas, they're taking the photographs of a type, not of the individual. And I wonder, how does one decide when a particular cloud is a type of cumulus cloud? When does it tick all the boxes that makes it a cumulus or stratocumulus or whatever else is they're trying to photograph? So in that sense, it seems like the knowledge about what constitutes a particular type determines the moment at which the photograph of a specific individual cloud is taken. And that then becomes the type. And it kind of promotes the kind of this fleeting cloud into a norm of what counts as a particular type. And I wonder if that can be expanded to other elements, like in snowflakes or whatever else is being photographed and used in meteorology.
That is an excellent question, and in fact, it's again something I go into in the book is how is the photograph used as scientific evidence? How do you believe it? So, for example, if we go back to the cloud, one of the examples I use in the book is, imagine you're out in the field and you're photographing a storm. And when you photograph the storm, let's say you have a camera, as many scientists do. There are many decisions that have to be made that could affect how that image is interpreted. Will everybody interpret that the same way? And that's not clear. But when you make that photograph of the evolving storm or a cloud, the question is, what lens do you use? Different lenses, wide angle versus telephoto, will change that perspective and the form of the cloud. When you photograph the cloud, and what kind of light? Is it side lit, backlit, or front lit? At what stage do you photograph the cloud? Where do you stand to photograph the cloud? The vantage point. Do you photograph it from the ground or from an elevated platform? So the question you raise is really at the heart of important scientific information. How do we interpret that? So once you make that image, then the question is, will everybody interpret it the same way? And maybe not. So there's this whole question of, like you say, at a particular moment, you may say, okay, there's a storm cloud or a thunderstorm. But of course, in science, we want to know, what is it about a particular thunderstorm, for example, or its case study that can tell us something that might be extrapolated to other storms. But in terms of the photograph, there's so much room for interpretation after the fact, and of course, how you made the photograph in the first place. And in fact, many papers up until recently really would not provide information about the photograph that was used in the paper. What lens, what aperture, what shutter speed, all this technical information. It's a little bit better now today with digital, because now we can get spectral information. So for lightning photography, the digital camera has been really helpful. But you're right, it's a qualitative call. I guess you have the cloud atlas, you make a picture, it's kind of like a police lineup. You match up the person and say, that looks like that kind of image. But beyond that, then of course, there are lots of these other questions about how do you interpret that photograph and gather and use it as a source of data in a sense. And that's kind of a challenge. And this whole notion of interpreting visual imagery is something that I go into in some depth of how do we, is seeing believing. How do we see this photograph? Is it representative? How do we measure it? What does it tell us? And how could hopefully, when several people observe the same photograph, they can draw the same conclusions, but it's not always clear. So, but really good point.
Thank you, Terry. Any other questions, please?
Irina, I think I'll go back to one of your question earlier. Maybe this might help too. There's a very famous photographer called Alfred Stieglitz. He was married to Georgia O'Keeffe, one of the most famous American artists. And Alfred Stieglitz really helped pioneer photography as an art form. Up until around that time, early 20th century, photography was kind of the stepchild of art. People said, how can you produce art with a mechanical device like a camera? But one of the projects he did was called Equivalence. And it's a sequence of photographs of clouds where he wanted to use clouds that would capture his innermost emotions and feelings. So he has this whole series of clouds, the project called Equivalence, where he was using the clouds, and some other famous artist commented that it was kind of like his symphony of the sky. But he viewed it not so much from the scientific perspective, but how could these various cloud types capture his innermost emotions and how he was viewing the world. So it's one of his famous projects called Equivalence. That is the equivalent between the cloud and his innermost feelings.
Thank you so much. I have just written to myself.
Yep, Alfred Stieglitz. Yep.
And Georgia O'Keeffe has done her own cloud.
That's right.
Her early paintings had a lot of cloud studies. Yeah, fantastic stuff. I'm just wondering, Terry, if you go back to the spectrum, a technical issue, and I was looking at the pictures taken on an ultraviolet part of the spectrum and an infrared ones, and you look at the photographs taken through the kind of ultraviolet, they look very similar to the kind of visual spectrum. They show the shape of the things that you're taking photos. Similar thing with the infrared. So when do we start losing the kind of familiar shapes if we move along the spectrum, and what starts to show up, if anything, that can be of interest to scientists if we leave the narrow band?
Yeah, those narrow bands or the windows that allow the radiation to pour in without absorption, that whole spectrum, that absorption spectrum, is really at the heart of understanding greenhouse gases and their effect on climate. So those spectral bands, those little windows, or the absorption bands, tell us so much about the constituent makeup of Earth's atmosphere and how that's changing. So that's one of those important things that's still important today in terms of research, and it was recognized way back when photography was beginning to making the first picture of the photographic spectrum. So I'm not sure if I answered your question, but those gaps are very important to tell us something about the signature of the atmosphere and its composition.
We have, let me check what's happening in chat. Yes, we have a quick message from Simon Gaskin here, thanking you for the wonderful talk. Let me see if there is anyone else out there who would like to ask anything, Terry, about photography, meteorology. Otherwise, if not, I would like to again thank you, Terry, for a wonderful tour de force of photography and meteorology. And before we leave the scene, and before we say goodbye to everyone, I just want to share you one quick screen, which is this one. This is for our next meeting, or upcoming meetings rather. The virtual meeting is going to take place on 5th of January, and our speaker will be Martin Young on the evolution of weather forecasting in the UK. But then on the 12th of March, I would like to welcome you to a in-person and streamed meeting on the history of climate science ideas and their application, which is taking place in London. And the information on this, on both of these events, is available at the World Meteorological Society web page. Here are the links. I'm not sure that you can take time to write them down, but if you go to the website, you'll be able to find among the meetings and other events these two things. And finally, please stay in touch with us, become a member, and follow us on various social media here on Twitter and Facebook. And at the bottom is our email. This talk will be shown on the Society's web page very soon. And again, coming back to full screen one more time. Thank you, Terry, for a wonderful talk. On behalf of the history group, I wish you a wonderful day, and please stay in touch. And thanks everyone for joining us tonight.
Well, thank you, Vlad. I really appreciated having the opportunity to speak to you and everybody there. I'm glad people were able to show up and hear the talk. And I know it's dinner time for most people, so hopefully you have a good dinner. But thank all of you for coming to the talk.
Fantastic.